Darjil Learning Hub welcomes the viewers for this new episode. Now in today's class, we are going to study the Bragg's law of X-ray diffraction, the Bragg's spectrometer, few applications of Bragg's spectrometer, and the Lawes experiment. All these things we are going to study here. First, let me explain what is meant by Bragg's law, which you may be very familiar in your lower classes also. Consider a monochromatic beam of X-ray. AB is the monochromatic beam of X-ray. When I say monochromatic, you will know the wavelength will be lambda. It is lambda, only one wavelength. And let small d be the interplanar distance of the crystal plane, and theta be the glancing angle. You should also know what is meant by glancing angle. Angle between the incident X-ray and the crystal plane is called the glancing angle. So AB is the incident beam of monochromatic X-ray falling on the crystal. After reflection, BC is the reflected ray. Similarly, you consider another ray, A dash, B dash. After reflection from the bottom of the crystal plane, it will also be reflected B dash, C dash. These two reflected rays will be interfering with one another by the different planes. And these two rays will meet together. There may be a phase change, or sometimes it may be in phase with one another, or sometimes there may be a phase difference. So these two rays will interfere with one another, and a path difference will be produced between the two rays. So if the path difference between the two rays is equal to even multiple of lambda by 2, then these two rays will be in phase with one another, and they will produce a maximum intensity. So this is the condition for interference of the diffracted rays. Therefore, let us take, what about the path difference between the two rays? A, B, C is one ray. A dash, B dash, C dash is another ray. If there exists a path difference between the two rays, and if the path difference is equal to even multiple of lambda by 2, they will be in phase with one another, and it will produce the maximum intensity. That is 2n into lambda by 2. 2n is for even. N will be equal to 1, 2, 3 and so on. Therefore, 2n into lambda by 2 equal to n lambda. So therefore, in short, I can say if the path difference is equal to n lambda, then you will have maximum intensity and the two rays are in phase with one another. So what is the path difference between the two rays? You draw a perpendicular line from B to A dash B dash, it is BD. Similarly, perpendicular line to B dash C dash, it is BE. Therefore, up to AB, A dash D is equal, BC is equal to EC dash. The extra path travelled by the second ray is DB dash and B dash E. This value is the extra path difference. Therefore, the path difference between the two rays is B dash D plus B dash E. B dash D could be calculated from the rectangle triangle. B dash D is a rectangle triangle. Therefore, from here, this is theta. Therefore, sin theta will be equal to opposite side divided by hypotenuse. Therefore, from here, B dash D will be equal to D sin theta. Similarly, for the next triangle also, B dash E will be equal to D sin theta. Therefore, the total path difference will be equal to 2D sin theta. If 2D sin theta equal to n lambda, then you will have the bright spot, and this is called the Bragg's law. Therefore, 2D sin theta equal to n lambda is called the Bragg's law. Now, what is the Bragg spectrometer? What about the construction of the Bragg spectrometer and how it works? What are the applications of the Bragg spectrometer? What about the construction detail and the working of the instrument? So now from here the figure shows the Bragg spectrometer. Here you have a Coolidge tube from which X-rays are produced. These X-rays are made as a fine beam by the two slits S1 and S2, and they will be collimated into a fine beam. It falls on a crystal placed on a vernier table of the spectrometer. This angle, glancing angle, could be measured by this vernier scale attached with the main scale here. At an angle of 2 theta, the collimator, or we can say this telescope, instead of the telescope we can have the ionization chamber. The ionization chamber could be placed at an angle of 2 theta to measure the reflected beam or the diffracted beam. Now this ionization chamber also, we have 2 slits, and through the slits the X-rays will be coming, and we have an ionization chamber. So therefore the gas inside this ionization chamber will be ionized, and we will have the ionization current. The ionization current could be measured by this electrometer attached here with. Now the crystal could be rotated by rotating the vernier table. So this is the Bragg spectrometer. Now this Bragg spectrometer could be used to verify the Bragg's law. The Bragg's law is 2d sin theta equal to n lambda. Whether it is true, we would like to verify it. Therefore, X-rays coming out of the Coolidge tube will be falling on the crystal placed at an angle of theta. From this angle of theta, we have the ionization at an angle of 2 theta. The intensity of the X-rays could be measured. Now the experiment is repeated for various glancing angle. For various glancing angle, we measure the intensity of the rays that is diffracted here, and we draw a graph. The graph would be as shown in the figure. So glancing angle versus the ionization current. Now on seeing this graph, we have seen 3 peaks intensities at certain angle. So from the graph, corresponding to the peak, we measure theta 1, theta 2 and theta 3. And if we calculate the value of sin theta 1 is to sin theta 2 is to sin theta 3, it is found to be 1 is to 2 is to 3. And that is our law. That is, this first one represents the first order one, second order and third order intensity. That is 2d sin theta equal to n lambda is verified. The second use of the Bragg spectrometer is we can also determine the wavelength of the X-ray. To determine the wavelength of the X-ray, once again the same experiment is done with the glancing angle. For various glancing angle, we can measure the intensity here. And now from here, using the formula lambda equal to 2d sin theta by n, theta is known. If n equal to 1, if you know the value of interplanar distance, then using this formula, one can calculate the wavelength of the monochromatic X-rays reflected from the crystal. The third example or the third application is we can also determine the interplanar distance having Miller indices HKL. HKL is called the Miller indices within the bracket. If we know these values, we can determine the interplanar distance also. Now let us take A as the interatomic distance between the lattice points, and D is the interplanar distance. Our aim is to determine the interplanar distance, and let us take, we know the value of interatomic distance, and rho be the density of the material, and m is the molecular weight, and n is the Avogadro number. From this one could easily find out the mass of the unit cell. How can we find out the mass of the unit cell? I am going to calculate the mass of the unit cell of the crystal by two ways. One is mass of one atom is determined here. In m kilogram of the substance, we have n atoms, capital N atoms, Avogadro number. So n atoms will have the molecular weight capital M. Therefore, the mass of one atom will be equal to m by n. If in a unit cell you have small n atoms, then the mass of the unit cell will be equal to n into m by n. Because m by n is the mass of one atom and n is the number of atoms inside the unit cell, in the unit cell. Therefore, mass of the unit cell will be equal to n into m by n. The same mass of the unit cell could also be calculated by the basic fundamental formula. Mass will be equal to volume into density. A cube is the volume of the cubic cell, rho is the density. Therefore, volume into density will give you the mass of the unit cell. Equating the two, A cube rho will be equal to nmn. Then from here, A could be calculated. That is, the interatomic distance could be calculated. So, knowing the interatomic distance and the formula for the interplanar distance for a cubic cell, the interplanar distance could be calculated as A divided by square root of h square plus k square plus L square. Therefore, using this formula, one could easily calculate the interplanar distance. And now, what is meant by the Laway's experiment? Laway performed this experiment the same as that of the Bragg spectrometer. He placed zinc sulfide crystal in the X-rays and he have the photographic plate, and he found that a central spot followed by the circle of low intensities, and these spots are called the Laway spots. Position represents different crystal planes. So from here he could understand that X-rays are electromagnetic waves and atoms are arranged in a regular periodic manner in the crystals, and he found out the lattice planes are at equidistant planes passing through the lattice planes. Miller indices are represented within the bracket as HKL. If it is placed inside a square bracket, it represents the direction of the plane. All these things could be explained by Laway's experiment. So, my dear students, hope that you would have understood the Bragg's law and the Bragg spectrometer, applications of the Bragg spectrometer and Laway's experiment to determine the interplanar distance also. Thank you for listening. Thank you.
இந்த வீடியோ உங்களுக்கு பிடிச்சிருந்ததுன்னா லைக் பண்ணுங்கள், ஷேர் பண்ணுங்கள், கமெண்ட் பண்ணுங்கள். இதே மாதிரி இன்னும் நிறைய வீடியோஸ் பார்க்கணுன்னா மறக்காமல் டார்ஜில் லேர்னிங் ஹப்பை சப்ஸ்கிரைப் பண்ணுங்கள். அந்த பெல் ஐக்கானையும் ப்ரெஸ் பண்ணுங்கள்.